Hello, everybody. So this is going to be section 3, and for me, this is where derivatives really start to get easy, and I think it's also going to get easy for you because we have a bunch of different derivative rules that we use, and they're all based in the idea of the definition of a limit. And just to recall the definition, f prime of x equals the limit as h goes to 0 of, well, I think I used a before, so we'll use f of a plus h minus f of a all over h. And these rules, like I said, these rules are all related back to this, but we're just going to go straight into the rules. I'm going to do a bunch of examples so you can see how to apply them. And you're going to see just how fast we can start doing derivatives with these rules. So the first rule we're going to go over is called the constant rule. Now, the constant rule says that if c is a real number, then the derivative of c equals 0. So if we think about this, this should make a lot of sense. Now, real quick, if I were to graph, let's say, a constant function. Now, we know c is going to be some function, and let's say we graph y equals 2. Well, y equals 2 is a horizontal line that crosses the y-axis at the y-intercept, 0, 2. And we know the derivative is the measurement of the slope. The derivative tells us the instantaneous rate of change at any point. Therefore, if you look at what we have here, a horizontal line, all horizontal lines have a slope equal to 0. So hopefully this rule, the constant rule, makes a lot of sense. The derivative of a constant is equal to 0 because the slope of this line is equal to 0 to begin with. Now, just for some easy examples here, if we wanted to find the derivative of 5, it equals 0. If we wanted to find the derivative of, I don't know, negative 15 equals 0. Even the derivative of e, which is approximately 2.71, that's still 0, okay? So there's our constant rule. Very simple, easy, straight to the point. The next rule we're going to go over is going to be the power rule. So the power rule just says if n is a non-negative integer, then the derivative of x to the n equals n times x to the n minus 1 power. So a really easy example of this would just be, let's find the derivative of x to the third power. Well, according to our power rule, what we need to do is take the power and move it out front. So let me get a different color here. So we're going to take this, put it out front, and then we subtract it from 1. And 3 minus 1 is 2. So our derivative is going to be 3x squared. So I'm going to do just a couple examples using this. So let's see, the derivative ddx of x to the 16th power equals 16x to the 5th. The derivative of, let's say, x to the 3/4 power is going to equal, well, you remember, you're going to put the power out in front and then subtract the power from 1. In this case, I'm going to be very clever on how I write the number 1. Instead of writing 1, I'm going to write 4 over 4. So that's going to give me 3/4 x to the negative 1/4 power. Okay? We'll do one more here. How about ddx of x? Well, remember, you pull the power out in front. So technically, there's a 1 here. So we can just pull the power out in front. And that's going to give me 1 times x to the 0. And as long as x does not equal 0, we get 1 times 1, which is just 1. Okay? Now, the next rule we're going to learn is the constant multiple rule. Now, this rule, we apply a lot, but sometimes once you get really good at this, a lot of people kind of just blow right through this one. But you should be all right with it. So if f is differentiable, meaning you could take the derivative, at x, and c is a constant, then what we could do is this. So here we have a constant times a function. Well, the constant multiple rule says we can take the constant and move it out front. And what we could do is find the derivative of the function of x and then just multiply by the constant at the very end. So an example of this would be something like this. Let's say I wanted to find the derivative of 3x to the 5th. Well, according to this rule, I could take the constant and pull it out front and find the derivative of just x to the 5th. So this is going to give me 3 times, now the derivative of x to the 5th is 5x to the 4th, and 3 times 5 equals 15x to the 4th. Okay? Another example of this would be something along the lines of how about ddt of 1/2 d to the, or I'm sorry, 1/2 t to the 12th power. So once again, we could just pull the 1/2 out front, because what we're really concerned with is finding the derivative of t to the 12th. The derivative of t to the 12th is going to be 12t to the 11th, and then 1/2 times 12 is 6t to the 11th power. Okay? So a lot of times, honestly, we really don't even, I know personally, I don't pull the constant out front, only because it's like more writing. So an easy way to kind of just visualize this, say we want to find a derivative of 10x to the 4th, I would just say 10 times 4x to the 3rd, which is 40x to the 3rd. Okay? Now, there are things that we can do with derivatives, which is pretty nice. We call a derivative is considered to be a linear operator, which means it follows all the properties of algebra. So we can distribute it. If we wanted to, we could factor it out. So we do have some rules. So I'm going to call this the sum or difference rule. And all this says is that if we have two functions, call them f and g, and they are differentiable, at some value x, then ddx of f of x plus g of x. In other words, if I wanted to find the derivative of two functions that I'm adding or subtracting, so subtracting also applies to this, then what you can do with the derivative is you can actually, or the derivative symbol, is you can distribute it. So we get ddx of f of x plus or minus ddx of g of x. Okay? And like I said, all this really means is that we can just distribute the derivative. So an example of that, and once you get, like I said, once you get good at this, you kind of don't do this as much, but it's good practice to understand when and why you can do it. So let's say we have the derivative of ddx of 2x to the third plus 9x to the seventh minus 4x to the third plus x. Okay? So what we can do is go ahead and distribute our derivative symbol to each one of these terms. So I'm just going to write this out real quick. And also, hopefully you could start to see that I can apply another rule, which is that constant multiple rule. So I can take the 2, pull it out front if I wanted to. Take the 9, pull it out front. Take the 4, pull it out front. Like I said, it's a lot of writing. And then from left to right, I'm just going to go ahead and take each derivative. So I get 2 times 3x squared plus 9 times 7x to the 6th minus 4 times 3x squared plus 1. And then just to clean this up a little bit in writing in descending order, 9 times 7 is 63, x to the 6th. 2 times 3 is plus 6x squared. Negative 4 times 3 is minus 12x squared plus 1. And then I can group like terms in the middle. 63x to the 6th minus 6x squared plus 1. All right. Now, the next derivative we're going to go over is it's actually a special case. Okay, it's a special case. So there's a number that we frequently see in mathematics, and there's 2 ways to define it. And that number is e. E is approximately 2.71828 and a bunch of numbers after that. I forget exactly what it is. But what I do know is there are 2 ways that we can actually define e. The first let me write it like this. The first way is to look at this quantity that we have here. So 1 plus 1 over n, all raised to the n power, is how we define e. Now, what ends up happening is if we let n go to infinity, then these values will start to approach 2.71828 and a bunch of other decimals after that. And hopefully it should kind of make sense because that 1 over n is eventually going to get to 0, and all you're doing is you're adding a little bit to the number 1, and then you're squaring it. So when we have the derivative of e, so that's what this rule is, the derivative of e, we'll call it e to the x. We say that the function f of x equals e to the x is differentiable for all real numbers x, and the derivative, so d dx of e to the x equals e to the x. And like I said, this is a very special case of the derivative. In fact, when we get into, what section is it? I think it's like section 5. Oh, no, I'm sorry. It's section 7, the chain rule. We're actually going to learn the general rule for the derivative of e to the x. But like I said, that's not until section 7, so we don't have to worry about that now. So the thing you got to remember, the derivative of e to the x is e to the x. Okay? So I'm really not going to do any examples of that because the derivative is the example. But what I'd like to do is I want to do just a bunch of examples using these rules, and I want to incorporate some of the techniques that we have to know how to do. So the first example I'd like to do is I want to write an equation of the tangent line to the graph of, and I'll write it down here, f of x equals 2x minus ex over 2 at the point 0, comma, negative 1/2. So you recall that anytime we see, write the equation of the tangent line. All right, so anytime you want to write the equation of a tangent line, you need basically 3 things. Now, earlier I said 2, but you also need another thing, which kind of goes without saying. So we need 3 things. We'll call them items. First, you got to have your slope at x equals some value. Second, you got to have a point. And then third, you're going to use the point slope form, where your slope is now the derivative evaluated at some specific value. We're going to call it a. So for us, I'm just going to kind of like draw a little line here because it's not going to take too much space. First, let's find the slope at x equals a. In this case, x is going to equal 0 because that is the 0 point, or that is the x component of my point. So the derivative f prime of x is going to equal 2 minus e to the x over 2. Because now, remember, e to the x, the derivative of e to the x is just e to the x. And that negative 1/2, you could actually, let me write it off here to the right so I can show you. Maybe I did that too fast. So when I want to find the derivative, the first part is just going to be a 2. Now minus, now technically, this is going to be d dx of negative 2. Oh, sorry, let me write it like this. Negative 1/2 e to the x. So I can pull that negative 1/2 out front. And all I'm doing is just taking the derivative of e to the x. We know the derivative of e to the x is e to the x, so it's just going to be minus 1/2 e to the x, which is exactly what I have right there. But now I need to evaluate this at f of 0. Well, e to the 0 equals 1. So this is going to be f prime of 0 equals 2 minus 1/2. To subtract, I need a common denominator. So we got 2 over 1 minus 1/2. Multiply the first fraction by 2 over 2. That's going to give me 4 minus 1 over 2, or 3 over 2. Okay? So in terms of the items that I need, sorry about that. In terms of the items that I need, I could put a check mark next to x equal, or the slope at x equals a. Now the point, well, the point was given to us, 0, comma, negative 1/2. So I could put a check mark next to that. So now I'm just going to use my point slope form. So y minus negative 1/2 equals 3 over 2 times the quantity, x minus 0. So from here, I'm just going to distribute. So that gives me y plus 1/2 equals 3 over 2x. And then subtract both sides by negative 1/2 to give me y equals 3 over 2x minus 1/2. And a nice, easy way to check yourself to make sure you are correct is all you have to do is just graph it. So what I'm going to do is pull up Desmos real quick. All right, first thing I'm going to do is let's graph our function. So our function is going to be y equals 2x minus, we'll put the e to the x in the numerator, and then put a 2 in the denominator. So that's what our graph looks like. The point in question is 0, negative 1/2. 0, negative 1 over 2. Oh, parenthesis in the wrong spot, but that's all right. We'll live. I'll go ahead and label this. So I'll just click on the label. Now, the equation of the tangent line that we found, and I already forgot what it is, 3 over 2x minus 1/2. Okay, so y equals 3 over 2x minus 1/2. And there it is right there. So I can kind of zoom in here a little bit. But eventually what ends up happening is the more you zoom in, the straighter the line is actually going to look. But that is exactly the point at which our tangent line just skims across our function right there. I think the key to everything here is just understanding, zoom out here a little bit, understanding what the question is asking us to do. Whenever you see the words, write an equation of the tangent line, you need 3 items. Slope evaluated at x equals a. And remember, the slope is now our derivative. 2, you need a point. They're either going to give you the point or they're going to say x equals 1. And if they give you x equals a number, then you're going to have to find that point. And then third, we just use y minus y1 equals the derivative evaluated at a times the quantity x minus x1. Now, there is one more thing I want to go over, and that's just the idea of higher order derivatives. So what you're going to learn in a little bit, once we get into like application problems and everything. So give me a second here. Let me just put higher order derivatives. Higher order derivatives. What you're going to learn is there's actually a relationship between displacement, velocity, and acceleration and their derivatives. So, for example, if you have, let's say, some function, let's call it s of t, okay, and that's going to equal, like I said, some function of t. Then the derivative equals the velocity. So in other words, the first derivative, of displacement is the velocity. Now, if you have the velocity and you want to find its derivative, that is equal to the acceleration. So if I come over here to the right, and this is, I'm going to need just a little bit of space. The second derivative of displacement, and then in parentheses, all right, which is the first derivative Oh, I hate it when it does that. Now I have to click on this and come back up because I don't know how to fix it. If any of you know how to fix that so it doesn't pop up anymore, I would love an email. So the second derivative of displacement, which is the first derivative of velocity, is the acceleration. All right. So what you could do is just write like a little, I guess, equation. S of t, which equals s prime of t, and s double prime of t. And what I'll do is underneath, I'm just going to put velocity, and then the derivative of that is our acceleration. Now, as long as you can take a derivative, you can keep doing this. The fourth derivative of displacement, and how we write that is we would go ahead and write it as Is it the fourth? No, I'm sorry. I think it's the third. Yeah. Triple prime. It's called a jerk. It's that tells you how fast is the acceleration changing and in what direction. So an easy example of this would just be something along the lines of a particle's movement, or a particle is moving and the displacement can be modeled by the equation S of t equals 4t to the third plus 2t to the second minus t plus 1. Find the velocity and acceleration at, we'll say t equals 1. Okay? So, if I want to find velocity, all I have to do is take the first derivative. So that's going to equal 12t to the second plus 4t minus 1. And I can evaluate that at 1. So that's going to give me 12 plus 4 minus 1. So the velocity at t equals 1 equals 12 plus 4 is 6 minus 1. I'm sorry, 12 plus 4 is 16. And 16 minus 1 is 15. And I don't know, we'll just say this is meters per second. Give it some units. I'll just make them up. Okay, but what's really important here is this. We know the velocity is moving forward. So this particle is moving forward. If it were negative, it would be moving backwards. Okay? Now, the acceleration is going to be the second derivative of displacement, which is the first derivative of velocity. So a of t, or the acceleration, is going to equal 24t plus 4. In other words, you just take your velocity equation, or your velocity function, and just take its derivative. So 12t to the second is 24t, and then plus 4t is 4. The derivative of a constant, which is negative 1, the derivative of that constant is 0. So we're just left with 24t plus 4. Now we're going to evaluate this at 1. So the acceleration is increasing by 28 meters per second squared. Once again, I'm just making up these units. That's all. It's 24 times 1 is 24 plus 4 is 28. And that is how fast you can really start to just do these types of problems, do derivative problems. The key is being able to apply the proper rule. So what I'm going to do here, I'm just going to do just a couple examples. I'm just going to show you how easy this is. I don't want you to get confused, so make sure when you write down the problem, you write it down correctly, and then you use the proper rule. So for example, the first one, let me just write directions. Find the derivatives for each function. All right, so the first one is going to be g of x equals e to the third. Well, you got to remember, e to the third is a constant. It's a number. It's just 2.718 raised to the third power. So the derivative is 0. Next one. How about f of v equals v to the 100 plus e to the v plus 10. So our derivative here, we're going to apply the power rule. So that's going to give me 100 v to the 99 plus the second part, we need to apply the exponent rule. So e to the v, its derivative is going to be e to the v. And then lastly, the 10, that is the constant rule. So that's going to be plus 0, or you don't even have to write that down. All right, next example. Now this one is going to look a little weird at first, but we can handle it. The function is f of s equals the square root of s over 4. So our derivative here is going to equal, now, what I'm going to do is I'm going to come off to the right-hand side here because I don't have a rule for a square root. If you look at those rules, we have like the power rule, the sum or difference rule, e to the x rule. We don't have a rule for the square root. However, a long time ago, you were taught that the square root is nothing more than an exponent that's a fraction. So by knowing that property, I can rewrite, I can rewrite f of s as s to the 1/2 power over 4. So my derivative here is going to be 1/4 out front times 1/2 s. And remember, you need to take 1/2 minus 1. I'm going to be just clever on how I write the 1, and so it's going to be 2 over 2. So this is going to be s to the negative 1/2. So now when I clean this up, it's going to give me 1/8 s to the negative 1/2, or f prime of s equals 1 over 8 times the square root of s, which is in the denominator. Okay? So just because you don't have an exponent, maybe you need to do a little bit of algebraic simplification in order to get it into a form where you can apply one of those rules. Now, speaking of maybe doing a little bit of algebraic simplification, you could have a problem like this. So when was that? C? Okay. So we could have this problem right here. F of x equals the square root of x plus 1 times the square root of x minus 1. So if you go through the lecture, even if you go through the book and the notes that you've taken, you really don't have a rule yet for two functions of x that are being multiplied. All you really have is the power rule, e to the x rule, sum and difference rule. And you got your constant rule. But all you got to really do is just take a step back and look at what you're given. Now, I don't know if you've ever heard this word before or not, but I'm going to just let you know what these are. These are called conjugates. And the reason why they're called conjugates is just because if you look at the terms, the first terms are the exact same. The last terms are the exact same. It's just they differ by signs in the middle. Now, one of the most popular ways that you have seen this before is over here on the right-hand side of your screen with something like x plus 2 times x minus 2. If you were to distribute, you would get x squared minus 2x plus 2x minus 4. Notice the key, these middle terms, end up canceling themselves out. That's exactly what's going to happen here with our problem. So, since we can recognize that we have conjugates, we don't have to go through all of the multiplication. All we have to do is just multiply the square root of x times the square root of x, which is going to be x, and then the square root of, and then 1 times negative 1, which is negative 1. And now when we take the derivative, we just get 1. That's it. So let's see here. The last example I want to do, actually, you know what? I'll do a couple more of these because there is another one. And more examples is always good. So let's try this one. So we're going to let y equal 12s to the third minus 8s to the second plus 12s all over 4s. So with a problem like this, you would need to first simplify. You got to use a little bit of algebra. Now, the denominator, well, that's a monomial. And whenever you have a denominator that is a monomial, meaning one term, you are allowed to separate every single term. So that's exactly what I'm going to do here. So I'm just going to separate and divide every single term by 4s. And when I do that, I end up getting 3s to the second minus 2s to the first plus 3. And now when I want to take the derivative, it's much easier for me. So I get 6s to the first minus 2. Derivative of a constant, which is at plus 3. Derivative of a constant is equal to 0. So it's just a 0. That's it. Those are the types of problems you're going to encounter, is you got to be able to simplify something. Okay? So I hope this helps. And in the next video, we're going to add onto our set of rules. We're going to learn about the product rule and the quotient rule. So I'll see you in the next video.